in cleanroom design, in which we establishing and maintaining an environment with a low level of environmental pollutants such as dust, airborne microbes, aerosol particles and chemical vapors. Designing the such sensitive environment like the cleanroom is not easy thing, but below 10 steps definitely helps you and define the easy way to design it. Most of the cleanroom manufacturer processes required the extremely stringent conditions provided by the cleanroom. Cleanroom design in each proper orderly way is very important, since cleanrooms have complex mechanical frameworks and high development, working, and vitality costs. Below steps present evaluating methods in cleanroom designing, people material flow in factories, classification of space cleanliness, space pressurization, space supply airflow, space air exfiltration, space air balance, variables to be evaluated, selection of mechanical system, calculations of heating cooling load, and requirements of support space. 1. People material flow evaluation layout. It is essential to assess the material and people stream inside the cleanroom suite. All critical processes should be isolated from personnel access doors and pathways. This helps cleanroom laborers because they are a cleanroom's biggest sullying source. There should be strategy for critical spaces, that is as compared to less critical spaces. The most critical spaces should have a single access to prevent the space from being a pathway to other. Some pharmaceutical and biopharmaceutical processes are susceptible to cross-contamination from other pharmaceutical and biopharmaceutical processes. For material process isolation, raw material inflow routes and containment, and finished product outflow routes and containment, the process cross-contamination needs to be carefully evaluated. 2. Identify classification for space cleanliness. It is very important to know the primary cleanroom classification standard and what the particulate performance requirements are for each cleanliness classification at the time of selection. It is very important to know the primary cleanroom classification standard and what the particulate performance requirements are for each cleanliness classification at the time of selection. There are different cleanliness classifications: 1, 10, 100, 1000, 10,000, and 100,000, and the allowable number of particles at different particle sizes which provided by the Institute of Environmental Science and Technology, IEST, Standard 14644-1. 3. Identify pressurization for space, keeping up a positive airspace pressure, in connection to abutting dirty or tidiness order spaces, is basic in keeping contaminants from invading into a cleanroom. It is extremely hard to reliably keep up a space's neatness order when it has unbiased or negative space pressurization. What should the space weight differential be between spaces? Different examinations assessed contaminant penetration into a cleanroom versus space weight differential between the cleanroom and connecting uncontrolled condition. These examinations found a weight differential of 0.03 to 0.05 in Wg to be viable in diminishing contaminant invasion. Space weight differentials over 0.05 inches Wg try not to give considerably better contaminant penetration control than 0.05 inches Wg. 4. Identify supply airflow of space. The space cleanliness classification is the primary variable in determining a cleanroom's supply airflow. Looking at Table 3, each clean classification has an air change rate. For example, a Class 100,000 cleanroom has a 15 to 30 AH range. The cleanroom's air change rate should take the anticipated activity within the cleanroom into account. A Class 100,000, ISO 8, cleanroom having a low occupancy rate, low particle generating process, and positive space pressurization in relation to adjacent dirtier cleanliness spaces might use 15 AH, while the same cleanroom having high occupancy, frequent in-out traffic, high particle generating process, or neutral space pressurization will probably need 30 AH. 5. Identify air exfiltration flow of space. The larger part of cleanrooms are under positive weight, bringing about arranged air exfiltrating into connecting spaces having lower static weight and impromptu air exfiltration through electrical outlets, light apparatuses, window outlines, entryway outlines, divider floor interface, divider roof interface, and access entryways. It is critical to comprehend rooms are not hermetically fixed and do have spillage. An all-around fixed cleanroom will have a 1% to 2% volume spillage rate. Is this spillage terrible? Not really. 6. Identify air balance of space. The larger part of cleanrooms are under positive weight, bringing about arranged air exfiltrating into connecting spaces having lower static weight and impromptu air exfiltration through electrical outlets, light apparatuses, window outlines, entryway outlines, divider floor interface, divider roof interface, and access entryways. It is critical to comprehend rooms are not hermetically fixed and do have spillage. And each fixed cleanroom will have a 1% to 2% volume spillage rate. Is this spillage terrible? Not really. 7. Assess remaining variables. Different factors waiting to be assessed include temperature. Cleanroom specialists wear frocks or full bunny suits over their normal garments to lessen particulate age and potential tainting. As a result of their additional garments, it is critical to keep up a lower space temperature for specialist comfort. A space temperature extend somewhere in the range of 66 F and 70 will give agreeable conditions. Humidity. Due to a cleanroom's high wind stream, a vast electrostatic charge is created. At the point when the roof and dividers have a high electrostatic charge and space has a low relative dampness, airborne particulate will join itself to the surface. At the point when the space relative dampness expands, the electrostatic charge is released and all the caught particulate is discharged in a brief time frame period, causing the cleanroom to leave detail. Having high electrostatic charge can likewise harm electrostatic release delicate materials. It is vital to keep the space relative moistness sufficiently high to lessen the electrostatic energized construct. A RH or 45% plus 5% is viewed as the ideal stickiness level. Laminarity. Very basic procedures may require laminar stream to lessen the shot of pollutants getting into the airstream between the HEPA channel and the procedure. IEST Standard IEST WGCC006 gives wide current laminarity necessities. Electrostatic discharge. Beyond the space humidification, a few procedures are exceptionally touchy to electrostatic release harm, and it is important to introduce grounded conductive deck. Vibration and noise levels. Some exactness forms are exceptionally delicate to clamor and vibration. 8. Mechanical system layout identification. Various factors influence a cleanroom's mechanical framework design: space accessibility, accessible subsidizing, process necessities, neatness arrangement, required unwavering quality, vitality cost, construction standards, and neighborhood atmosphere. Not at all like typical AC frameworks. Cleanroom AC frameworks have considerably more supply air than expected to meet cooling and warming burdens. Class 100,000, ISO 8, and lower OSH Class 10,000, ISO 7, cleanrooms can have all the air experience the AHU. Taking a gander at Figure 3, the arrival air and outside air are blended, separated, cooled, warmed, and humidified before being provided to terminal HEPA channels in the roof. To forestall contaminant distribution in the cleanroom, the arrival air is gotten by low divider returns. For higher Class 10,000, ISO 7, and cleaner cleanrooms, the wind currents are too high for all the air to experience the AHU. Taking a gander at Figure 4, a little part of the arrival air is sent back to the AHU for molding. The rest of the air is come back to the course fan. 9. Perform cooling heating calculations. When playing out the cleanroom warming cooling computations, think about the accompanying. Utilize the most moderate atmosphere conditions, 99.6% warming plan, 0.4% dribbled middle wet bulb cooling stoop, and 0.4% wet bulb middle dribble cooling outline information. Incorporate filtration into figurings. Incorporate humidifier complex warmth into figurings. Incorporate process stack into figurings. Incorporate distribution fan warm into estimations. 10. Mechanical room space fight. Cleanrooms are mechanically and electrically concentrated. As the cleanroom's tidiness arrangement moves toward becoming cleaner, more mechanical framework space is expected to give satisfactory help to the cleanroom. Utilizing a 1000 SQFT cleanroom for instance, a Class 100,000, ISO 8, cleanroom will require 250 to 400 square feet of help space. A Class 10,000, ISO 7, cleanroom will require 250 to 750 square feet of help space. A Class 1000, ISO 6, cleanroom will require 500 to 1,000 square feet of help space, and a Class 100, ISO 5, cleanroom will require 750 to 1,500 square feet of help space.